Alrighty, good morning, afternoon, evening, whenever you're choosing to watch this. My name is Jess, and I'm going to be going over Experiment 10, Enthalpy and Neutralization of an Acid and a Base for the Chem 1411 labs at TAMUCC. So, quick announcements before we get started. I just wanted to talk about this. Some TAs have been talking about the quality of labs have gone down a little bit. We totally understand that this time is really trying, but we are also trying to give you guys points. So remember that while you're doing these labs, try and make sure you're doing them at the same caliber that you would do in lab to the best extent possible. So make sure you're putting units during your calculations, you're citing your sources, things like that. Make sure you have a discussion at the end. And if you need help discussing, reach out to your instructor as well. If you're having trouble completing things due to issues back home or anything involving your family, please reach out to us. We do want to help you, and we do want to be flexible during this time. It's really challenging for everyone, so we can definitely help and find some alternative thing or give you a little bit of time if you need it. So just reach out and talk if you need it. The lab final exam after this is going to be the last thing you guys are going to do. So we still don't know when it's going to be. We are going to give you as much notice as we can. We're just in the process of determining that. Just make sure if you anticipate needing anything as far as accommodations, please reach out to your instructor as well as the services on campus and see how we can work out any accommodations remotely if we need them. And then the last thing, this slide, we have the pre-lab question you are to complete. So just make sure that you fill that out in your pre-lab section in addition to your background. So getting into the lab, we're going to talk about enthalpy and heat. They're similar but different, and it's important to know the difference. So heat, represented as a lowercase q, is thermal energy, or the energy transferred as a result of the difference in temperature between a system and its surroundings. And those two words are really important because when you're doing this math, you have to understand, are we looking at the system or the surroundings? Generally, when we're actually doing the math, we want to know the system, but sometimes we can only record the surroundings based on just technological limitations. So you have to know, whether your energy is moving to the system or out of the system, so if it's getting hotter or colder, and that's going to indicate the positive or negative value. So in this case, we can see on the screen the system is negative, the surroundings are positive, so the system is losing heat to the surroundings. Enthalpy is represented as delta H. Delta is generally the change in. So delta H is the energy associated with breaking and forming bonds in a chemical reaction. Key phrase, at constant pressure. So when you're setting up an experiment, we have to make sure the constant pressure is there so that we can accurately or efficiently determine our enthalpy, since that's part of the definition. It's sometimes reported as per mole of a substance, which we're going to be using today in our calculations, but generally it's reported with kilojoules or joules. And this figure here shows the enthalpy of H2O as a liquid. It's probably it getting vaporized. So it takes negative 285.8 kilojoules per mole to vaporize the H2O. So what that means is that 285.8 kilojoules of heat are going to be released. That's why it's negative, because we're releasing them to the surroundings. The system is losing that heat when 1 mole of H2O is formed. Sorry, this is not the vaporization. This is the creation of H2O. And we're going to put delta H at the end of balanced equation when we're competing things, and then you can use that in math later on. Most likely you're seeing that in lecture, or you will see it in Chem 2. And at constant pressure, we know that Q is equal to delta H. The last thing, and I've already mentioned these, joules, represented by a capital J, is just the SI unit for energy. So we have kilojoules, works the same on the metric scale as any of the other prefixes do. So commonly we're going to see our standard enthalpy values represented in kilojoules. So we want to go through that with our math there. So measuring enthalpy and heat, To do that, we use something called calorimetry. It is the method where you measure the heat involved in a chemical reaction or a physical change, whatever you want to observe, and it sets up an area of constant pressure so that you can record this. Using those principles and what we know about calorimetry, we can apply the definitions and whatever we record to the Q equals MCAT equation. And what that is built up of is you have Q, which we talked about before, that's the calculation for heat, and it equals to M for mass in grams, C, which is the specific heat capacity of your substance, and then delta T, which is the change in temperature. So one thing to note about specific heat, while mass you're going to collect and delta T you collect, C, or the specific heat capacity, is a constant, but again, it's dependent upon what substance you're looking at. So sometimes problems might give you a few specific heat capacities. Make sure you know what your substance is. Generally, you're going to be working with water, like we are today. That's the end product of our reaction. So we're going to use the specific heat capacity for water. It can be represented in kilojoules per grams delta C or joules per grams delta C. And what it actually means, as the units are saying, it is how many joules or kilojoules, how much energy it takes to heat 1 gram of your substance by 1 degree Celsius or Kelvin, whatever you decide to use in that situation. So down below, this shows our calorimeter, which is what we're going to be using in our experiment. It has a thermometer stuck down through a hole into a chamber where we're going to combine HCl and NaOH. As you guys saw before, which I think you got the chance to see those two react, you know that it turns into a salt solution with water because it's an acid-base reaction. But it's exothermic, so some heat is going to happen, and we are recording that temperature change. So one thing to note here, like I said before, we have to know what we're actually measuring. So in this situation, we're measuring the surroundings, and so we want to actually calculate for the system. So when we go to do our math, our Q surroundings is positive. We're going to have to apply a negative sign so that it's equivalent to the Q of the system. So essentially, you're going to just do all your math and then stick a negative sign in front of it. I'll go over that when I do the actual math as well with you guys. So the experiment that we did is we performed 2 trials of measuring the temperature change of that combination of those solutions, and we calculated Q and delta H from the process. We are assuming that the solutions are 1 molar each, which is going to be helpful for your calculations as well. And you're going to use the mass of each solution to determine the mass of what you're using in total, the mass of the water that you've made. And we're going to go calculate everything. We want, because of the situation and campus getting locked down, we didn't actually get to record this one for you guys, but we found a YouTube video online. That's going to be, the link is placed in the description of this video as well as on your document. So right now, I'm assuming that you guys are going to go click that and watch that. So I might reference some things that they did. So make sure if you're able to just pause that, watch that video, and then come back for the rest of the calculations. Just note that what they're doing is slightly different than what we did as far as data recording, but it's the same general principle. And when you come back, we're going to go through the math. Alrighty, so welcome back if you did go and watch that video. If not, I highly recommend it so you have a better visual and you may answer some questions that you might have. So I'm just going to give you a quick overview of the data table. We took data from some students from last year for this experiment, so this is real data, not fake one. So we have the mass of our NaOH and the mass of our HCl separately that were weighed. And then you have, when you add them together, you get the final mass of your product, which if you look through a balanced equation that you make up for your lab, you can see that that is supposed to be your water. we have the initial temperature and the final temperature of each trial, and you're going to go ahead and calculate the total temperature change that we saw. We have Q, which you're going to calculate from everything beforehand, and then we have the moles of H2O that you're going to see, and then the last column is the delta H. So you're going to run these calculations twice. We're going to average them together, and then you are going to be given the theoretical delta H, which is about 57.9 kilojoules per mole. Sorry, I think negative 59 kilojoules per mole. And you're going to compare that to the answer you got and get a percent error, and then explain that in your discussion, talk about how accurate the work was, precise, etc., and things like that, and then you're going to answer those post-lab questions that I'll show you at the end. So let's get started with the calculations. Okay, so remember our goal was to find delta H, but we have to work backwards because we don't have everything, right? We want to know Q of the system before so we can get to delta H, but our Q equals MCAT, since we recorded from the surroundings, is going to calculate the surrounding Q. So we're going to have to do a really easy conversion to get that out. So we'll start real quick. We know the mass. We're going to add these together to get the total mass, which is going to be 53.25 grams total. And we can take our delta T, which is just going to be the 28.5 minus 23.0 degrees Celsius to get to the 5.5 degrees Celsius. Since we're subtracting and we have one decimal place, that's why we record out to just one decimal place and not the 3 significant figures that each of these are. And we know M. I'm going to use the 0.004184 kilojoules because I don't want to convert later. Remember, it's standardly represented in kilojoules rather than joules, but we could also use the 4.184. It's preference, but I'm going to use this one here. So let's get started. So our Q equals MCAT. We're going to take the 53.25 grams times our 0.004184 kilojoules per grams Celsius times our delta T, which is 5.5 degrees Celsius. So, important to note, I always recommend this to my students to keep their units in their calculations because it makes it easier for you in the end. You don't have to memorize what units go with Q. A lot of students think that you have to do that. But if you keep your units as you go and you know how to cancel them out and manipulate them throughout, it's just algebra, then you're able to associate the units with this. So grams are going to cancel out because we're dividing over here, and same thing with Celsius. So our Q is going to be left in kilojoules. So once we do all this math, we are going to get an answer of 1.2254 kilojoules. And since we multiplied, we have to follow our significant figure rules. We had 4 sig figs here, 4 sig figs here, 2 here. So we're going to round to 2 significant figures. 1.2 kilojoules. You're going to do this twice because you have 2 trials, right? So make sure you do this twice. Same thing with everything else. Remember also, this is Q of our surroundings. We want to know Q of systems. So a positive Q of surroundings equals negative Q of systems. So to get the Q of our system, we just make this negative. Cool, so we have our Q now. You're going to run that twice, you'll have both Qs. So now can we calculate delta H? We're almost there, but remember that delta H is represented in some cases kilojoules per mole. We just need to know how many moles we've created. So to know the product truly and to know some molar ratios that are important, we need our balanced equation. So we combined HCl in liquid form with NaOH, also a liquid. If you know your acid-base reactions, you can probably guess this easily, but if you don't, we can determine it as well. So normal double displacement kind of idea, we take our cation and the alternating anion, so we get NaCl plus the cation and anion that are left over. So that's going to be H plus and OH minus, which when we write it better is just H2O. We know H2O to be a liquid, and if we looked at a solubility table, we could determine this, but you should also know this just from general life. NaCl, or salt, dissolves in water. So it's going to be aqueous. All right, so let's make sure it's balanced. We have one sodium, sodium, chloride, chloride, and this is going to be, we have two H's and then one oxygen here. So we've got a 1:1 to 1:1 ratio, all set to go there. Now what we're going to do is determine how many moles of water we had. The trick with this is which reactant produces less water, because one of these is going to limit the production of water, right? And we can't tell based on this. So we're going to have to use the limiting reactant ideas, which you probably talked about in lecture, to determine what we need, right? So I'm going to start over here. You're going to do this for each calculation. So in a way, you're doing 4 calculations total. 1 for HCl, 1 for NaOH each time. I'm going to start with with HCl. It really doesn't matter what you start with. So we're going to take the mass of HCl, and we want to know the molar, how many moles of H2O we have. So we know our mole-to-mole ratio, so we can work backwards. We know the concentration of HCl, which is moles per liter, so we have moles, right? And we need to know the volume of HCl. So we can take a mass and turn that into a volume using the density as a conversion factor. So the the density of 1 molar HCl is 1.02 grams approximately. And we know that there's 1,000 milliliters in 1 liter. And this was 1 molar HCl. And it's a 1:1 ratio. So we can calculate how many moles we had, and then all of this will cancel out accordingly. We're going to end up with 0.02569 moles of H2O, and that is 4 decimal places that we originally have. Now we're going to go ahead and do the same thing with our NaOH. The only thing that changes is the density. So it's 1.08 grams of, NaOH per 1 milliliter of NaOH. And same deal as last time. One mole of water is produced for every 1 mole of NaOH that's put into the system. If we had different coefficients here, these molar ratios would change. So you can't always assume it's a 1:1. It's going to result in 0.02505 moles of H2O. Look at these, they're really close, which makes sense because we're only about a gram off here, but the details are important. So we've produced less H2O using the NaOH. It's kind of surprising because we had more NaOH, so you can't always assume that the lesser reactant produces the limiting reactant here, right? So NaOH is our limiting reactant here. So now we can take the moles of water and trust this amount produced here. Remember, you are going to do this twice for your other trial as well. Now we can determine delta H because we have our Q and we have how many moles we used. So delta H is going to be equal to that negative 1.2 kilojoules over the 0.02505 moles of H2O. It's going to equal approximately negative 47.9 kilojoules per mole. And since we're dividing, we have 2 sig figs here and 4 sig figs here. We're going to round to 2 significant figures. This will be negative 48 kilojoules per mole. Now, when you're interpreting your results in your discussion, make sure you talk about what that means for delta H to be negative. Really important concept there for this whole calculation. You're going to find this number twice and take the average. And that's what you're going to use as your final average delta H answer. And then what you need to do as well is compare it to the theoretical, what you should have gotten, or what this group should have gotten, and perform a percent error. So remember, percent error is the absolute value of the measured minus the theoretical over the theoretical times 100%. We'll throw our numbers in here. So absolute value of negative 48 kilojoules per mole minus negative 57.9 was our theoretical in this lab, all over negative 57.9 kilojoules per mole times 100. We're going to get an answer of 0.171 times 100. These all cancel out because we are eventually dividing. So you're unitless, and then times the 100%, which is where you get your percent. It's going to be equal to negative 17.1%. The negative here isn't as crucial because you're just saying we were 17.1% away from the answer either way. So just realize that when you're interpreting your results, you had a 17.1% error. So go ahead and plug in your values. Make sure to run them twice where you need to. This next slide here is the data that you have. So it's just the same data table. You'll see everything I used. Make sure you fill in the final mass, the temperature change, the Q, delta H, and then the number of moles you needed. You're going to take the average at the end and then find the percent error of both. And then lastly, just as you have before, make sure you write a discussion, answer the post-lab questions that we give you, and then turn that into your instructor via email. Thank you so much for being flexible and doing your work. You guys have done a great job, and we're so sorry about the situation and hope that you're all well. And if you have any questions about the final exam, just make sure you email your professor. Thanks so much for tuning in.